was used for like a cryogenic application, so to come close to absolute zero. As I already mentioned, there is gadolinium was kind of the first material which was ever used. So cores that to form these phases that you want to achieve, you need a heat treatment at more than 1000 degrees for several days.
Hi, Sandra and Christina. Welcome to the podcast Everyday Metallurgy.
Thank you.
Hi, thank you for the invitation.
Today we're going to talk about a material that if you are stopped by the police and asked to say this word, they can check if you are drunk. Because we're going to talk about magnetocaloric materials. Say that fast 3 times in a row and you are allowed to drive again. But will you give a short introduction to yourself, what you're doing and where you're from? Sandra, will you start?
Yeah, thank you. So yeah, once again, hi to everyone, and thanks a lot for having us here in your podcast. We are very excited to talk about this topic that usually people don't know much about. At conferences, we always ask who has ever heard of that, and usually it's not many people. My name is Sandra Wieland. I studied materials science in Dresden, in Germany, like 10 years ago. I finished, and after my studies, I joined Fraunhofer IFAM in Bremen, and I guess most of your viewers are familiar with Fraunhofer. This is a very large German research association for applied science. And the IFAM is one of the Fraunhofer Institutes, so the Institute for Manufacturing Technology and Advanced Materials. And as the name already says, we offer quite a lot of things related to manufacturing. So we do material development and shaping for metallic, polymeric, and hybrid materials. Also, for example, batteries. So really all different kinds of materials, but also a lot of adhesive bonding and surface technology. But I, myself, and also Christina, we are both in the Department of Sustainable Powder Technologies.
Yeah,
and that's
powder metal is the winner.
Yeah. So, we look into all kinds of powder-based shaping technologies. And when I just joined the IFAM 10 years ago, it was a time when just the question came up if powder technology would not be beneficial for magnetocaloric materials. And so this came together, and I took over this topic of PM shaping of magnetocalorics. And this was my focus of research and my topic. In 2019, I also finished my PhD on sintering of magnetocaloric lanthanum iron silicon cobalt alloys.
That's
the challenge.
That's the real test.
That's the challenge.
And since that, I'm working on this topic together with Christina during the last years. So that's why she's also here, and we're doing this together as we are a team at work, and wanted to be also a team here.
A strong team. Christina, a few words about you?
Yeah, sure. First of all, thank you for having us. We are really very excited about it because nobody ever asked about magnetocaloric, so we are really happy when somebody starts to listen. So I'm Christina Beltner. I am also a mechanical engineer, and I have a special focus on material science. I studied at the University of Bremen in Germany as well, where the Fraunhofer IFAM is also situated. So basically next to the university, you will find Fraunhofer. And I am here as a full-time employee since 7 years already. It's quite a long time. And actually, I was working as a student before for Sandra for her PhD as well to support her. And it was also the magnetocaloric subject that drew me to drew me to powder metallurgy, basically, because I thought, okay, that's a fancy topic. I've never heard of it. let's start learning things about it. So in the last 7 years, I, of course, always focused on powder metallurgy as a whole. But as you know, you have a lot of different topics in it, and I specialize on the extrusion process of metal powders, which I think, Peter, is known to you, the process itself, and also, of course, on the shaping of this magnetocaloric materials, because it does come with some challenges, let's say it like this. And since beginning of the year, I am the head of the group of composite technology, and there we focus on the mixing and netting and compounding of composite material, which is powder metallurgy as well, right? Before you shape it, you have to develop some kind of feedstock. So basically, this know-how goes into a broader product range. So we not only do the powder metallurgy sintering route, but we also do highly filled polymers that are not being sintered after shaping. So they stay basically within their polymer matrix, and they are parts as is. So they're not sintered afterwards. They can be used for like conductive polymers or EMC shielding, as example.
So I have been working a little with magnetocaloric materials many years ago. We were trying to build a refrigerator that could cool down. And as we at Syntex are working a lot with magnets, we should build a monster magnetic system to do this. But I never really understood the fundamental of these magnetocaloric materials. So can you give an introduction to how they work and why they work?
Yeah, let's try.
Yeah.
So at first, maybe there's a really simple definition of magnetocaloric materials. These are materials which change their temperature when they are magnetized or demagnetized. So when they go in and out of a magnetic field. So this is the very simple definition. And maybe Christina can show a picture where you can also see a little bit what happens.
Yes.
Thank you. Here you can see the principle in the picture. Yeah. Exactly. Here we have the principle. So compared to a compressor, actually, because most people are familiar with that, so they maybe understand it more easily in the comparison. So you have your magnetocaloric material, and when it's not in the magnetic field, it has a certain temperature. Then you magnetize it, so you put it into the magnetic field, and the magnetic moments align. So, and by this, the entropy changes. So the entropy goes down when something is aligned. But in this case, if you say the entropy is constant, then to account for this change in entropy, the temperature goes up. So the material heats up to keep the entropy constant.
Yeah.
And the material is getting warmer. And more or less the same thing backwards is happening when you put the material out of the magnetic field. So the magnetic moments de-align, and to keep the entropy constant, the temperature changes, it goes down. And if you take away the heat or the cold, which is generated, and after heating up, you put the material back to its original temperature, then you can, when it cools down, when it gets out of the magnet, you get to a temperature which is colder than before. And then you take away the cold to a cold side heat exchanger, and get back to the original temperature. And this process you do in a cycle again and again and again. And so you can actually cool something or heat something up with a magnetocaloric material. So by cycling this process.
Yeah. And there's something with the Curie point of it that
Yes.
Also plays a role. Can you describe a little about that?
Exactly. So in principle, you could say that every material more or less is magnetocaloric. So for most materials, there will be a very small change of temperature if you put it in a magnetic field or put it out of the magnetic field. Mm-hmm. So this is just an intrinsic material property. But this change is usually very, very small and you are not able to use it. Mm. But if you do this at the Curie temperature of the material, you have a very high change in magnetization when you magnetize or demagnetize the material. Mm. And so you get at the Curie temperature, you get the highest magnetocaloric effect that the material can have. Mm. Okay. And so if you're at the Curie temperature or in the range of the Curie temperature, you can actually use this effect for cooling or heating, which would not be possible if you just use it at any other temperature. And actually also the first material where the magnetocaloric effect was found was nickel at its Curie temperature. So it was not a kind of special magnetocaloric material which was looked at first, but it was nickel, and there it was first seen that this effect existed. And this was almost 100 years ago, so it's quite well known actually.
Yeah.
And I think it's also quite important to note that when you look at the Curie temperature of this magnetocaloric material, that is always in a very low end of the spectrum, let's say like this. So it's like in the working range that where you would like to place the refrigerator. So we do not have materials that have a Curie temperature, I don't know, of 700 degree or 800 degree, because I mean, that would be a refrigerator in hell. and we are not, basically. So we always work with material, depending on the application, of course, with a Curie temperature usually between -10 to 30, 40 degrees, something like this.
And these materials that are used today, what are they and how and when were they discovered?
So maybe looking into the history a little bit, as I already mentioned, the effect itself is quite old or well known for a long time. And at the beginning, actually, it was not used for room temperature applications. It was used for like cryogenic applications, so to come close to absolute zero. And during this time, of course, as Christina already said, they needed other materials which have their Curie point very close to absolute zero or at very low temperatures.
Yeah.
And that was the first application, and actually they really could reach temperatures below 1 Kelvin, which was not possible before they applied the magnetocaloric effect. And just around in the 1970s, actually, it was the first time when they started to use it for room temperature applications and to find materials which are applicable at room temperature. And the first material which was used was gadolinium, which is a rare earth material, for those who are not so familiar with it. And actually, gadolinium has its Curie point around room temperature. And so you can very nicely use it in this temperature range. And all the first demonstrators or prototypes for room temperature magnetocaloric cooling, so a fridge, for example, they were from gadolinium. And from that on, it was further developed, and they also found other materials that are used today.
I remember in the project where I participated, we were playing with a material where we could adjust the Curie point. So when it became cooler and cooler, we could add another segment of the material that was designed for a lower temperature. Is that also what you do?
So actually, we at our institute, we are not designing the material, but we use materials that are already existing and do the shaping. But we are looking into materials which have this kind of cascading, is it called? So where you use different alloy compositions and have them one after another. And the reason why this is so important, maybe Christina can show the overview over the materials that are existing for magnetocaloric. We have a little picture just that you can see something when I'm talking about all these material names. Maybe makes it easier. So as I already mentioned, there is gadolinium was kind of the first material which was ever used. And gadolinium has a nice magnetocaloric effect at room temperature, but its effect is not very high. It's a very broad effect through a lot of different, or it has a broad temperature range where it's actually working, but the effect is not very high. It's a so-called second order magnetocaloric material. And after using gadolinium for quite some time, they discovered that they can use some gadolinium alloys, which have a much higher effect, magnetocaloric effect at their Curie temperature, but it becomes spike-like. So it becomes very narrow, the effect or the temperature range, but the effect is much higher. And this is called a first order magnetocaloric material. And there you have only, sometimes only 1 or 2 Kelvin temperature range where the material has a very high effect. So to make a fridge which needs to work in between, let's say, 5 and 30 degrees, you need several of these materials, and always one which has its Curie temperature at 5 degrees, one at 7, one at 9, and this is this cascade that you're building, always by adjusting the composition a little bit. And that was first done with the gadolinium alloys, but there was always the problem that gadolinium as a rare earth is really expensive and rare. And it was always not really a good thing for broad application. And then people came up with 2 other classes of alloys, and these are these manganese, iron, phosphor, silicon alloys, and lanthanum, iron, silicon alloys. And there are some more elements more thrown into this. And those 2 alloys also have this first order magnetocaloric effect, so a very high effect at a special temperature. But to really use them, you also have to do this cascading of the composition. To really build a fridge with it.
I remember, I think it was the lanthanum iron silicon we used. That was adjusted slightly in the chemical composition to do that.
You can. I think this is like the most used today. I would say is the lanthanum iron silicon alloy, and then you throw into this some cobalt or some manganese or some cerium and all of different things to adjust the Curie temperatures.
Basically, it escalates very quickly when it comes to adjusting the Curie temperature with other elements. And that makes it so challenging to find the right kind of composition and alloy to have a certain effect, and always a stable effect as well.
I can see that you have a line here about production and shaping, and it's so easy to do with gadolinium, but it seems more difficult with the lanthanum based. Can you dig a little deeper into how they are produced or designed?
Maybe I can first say why it's so difficult, or why there's a minus. So the lanthanum based and also the manganese iron based materials, those are intermetallic phases that you want to produce, and so they are very brittle materials, and it's difficult to form these intermetallic phases that you want to achieve. And so these are the two problems basically. So if you have to do a very long heat treatment if you cast them, these kind of alloys, then the microstructure is so coarse that to form these phases that you want to achieve, you need a heat treatment at more than 1,000 degrees for several days. Oh. And this is not so useful, actually. And then what you get during cutting the material, of course, you cut a lot of it away, which is also not so nice. And then at the end, you have a really brittle material which will easily break during cutting. And so all of these factors make it really difficult to produce this material or shape it. And but they are also, all of these are good reasons why we use powder metallurgy, actually. Because with the phase formation, you can be much faster if you use, for example, atomized powder. Gas atomized powder has a very, very fine microstructure because it cools down so fast. And there you can do the heat treatment in 2 or 3 hours instead of several days. So it's much faster. And also you don't have these problems with the brittleness. Because you can have a near net shape or a net shaping with different methods. And so this is really beneficial for this kind of alloys. And not only we are looking into this, shaping it with PM methods, but also a lot of groups actually, or a lot of groups is maybe too much said. It's
several.
Magnetocalorics, there are not so many at all, but it's many people have seen that this is a beneficial idea at this point.
And I think
I also sorry, Christina, I remember that surface area to get the heat in and out of the material. A big surface area is also important, and if you just cut or if you cast, you're limited in your flexibility in designing large surfaces. So powder metal routes can also do that. And I guess that's also what you're trying to design.
Right. Maybe we can get a step back just to explain why it's so important to have a high surface, as you said it already, to get the heat out and in. But maybe we can actually we have a short video of the of one machine that we built, a prototype machine in a public funded project. And maybe then you can better see why it's so important to get the heat out and which kind of shapes we are looking for. Maybe then people can understand better what we're talking about.
May I put in a word?
Yes, Christina.
So maybe it's a bit hard to understand how this material works because there's only a certain phase in the material, in all those alloys, that has a magnetocaloric effect in the way you would like to have it. So that's why you have to heat treat it. And that's why if you just cast it, like you take all this Lafayette material and you just cast it into a heat exchanger, it won't do a thing, basically. So because you have to heat treat it a certain way, that's why you're doing all of this, to get this magnetocaloric active phase in order to have a cooling or heating up and cooling effect. And that's why if you go back to the powder metallurgy route, you have to understand it's the same for the alloys that you're buying as a powder. So you buy the powder, it's a Lafayette alloy as example, and you take this powder, and when it's delivered, it does not have any magnetocaloric effect that you can use. It's not like this, unfortunately. So we take this powder, we shape it, and then we do the heat treatment, which is way shorter than for casted parts, as Sandra said already. So I think this is a very crucial step for outsiders to understand. So why are you doing all of this? I mean, you have the material, buy the material. Why don't you just shape it and, you know, get over with it? Because that's basically not how it works. I just wanted to throw this in for some context for everybody to understand.
Yes. So this was actually a prototype we built. Maybe you can stop it for a sec so I can explain a little. Yeah, this was a prototype that we built in a public funded project, or actually we delivered the material, magnetocaloric material, and our project partner, Christian Vogel, with his company GSI, they built this prototype. So what you see here is you have the magnet, or the big magnet array. That's exactly what you're talking about, or what you said at the beginning. In this case, we need a field of around 1 Tesla to really get a good working machine. So it's not like we take a fridge magnet and have it at the magnetocaloric material. We really need a big magnet array, which has this magnetic field, also homogeneous field. Around 1 Tesla usually is what we need for these machines. So you see the magnet array, and then we have the magnetocaloric material. In this case, in this machine, there are 2 casings with magnetocaloric material. You will see this. Maybe we can start the video again.
Can you see my mouse indicator?
Yes.
Yeah. Okay. So basically, this is the magnets here.
Yeah.
And the highest magnetic fields you will have here. Okay.
Yeah.
And that's the point also where you have a translative movement and how the magnetocaloric material is put in and out of the field.
Yeah, exactly. That's what you see here. And here you see the magnetocaloric material. So this is actually, we built this with laser melting in this case. And you have 2 magnetocaloric materials. Always one is in the magnetic field and the other gets out at the same time. And then what you see here also is the piping where water flows through. And here you see once again how it works as schematically. So the magnetocaloric material gets in the magnetic field, heats up, and then there comes a fluid transporting the heat away. And this fluid for magnetocaloric materials, it's usually just water with some anti-corrosion agent, but it's just water, takes the heat away, then the magnetocaloric material gets out of the magnet, cools down, and once again you have the water to transport the heat or the cold away. And that is how the machine looks like. And you can imagine that the faster this movement is taking place and the more often you cycle the magnetocaloric material, the more heat or cold you can generate, the more cooling power you get. So frequency is really important in this case. And to achieve a high frequency in this machine, you need to be able to get the heat or the cold out really fast of the machine. Yeah. So that is why we need this magnetocaloric material as a heat exchanger structure. So we need, usually what is said is we need fine channels and also very thin walls between these channels. And the walls should have around 500 micrometers or below. And the channels should also have a size of around 500 micrometers or below. And I mean, these are sizes which are achievable to cut when you have a material that cuts really nicely. But if you want to do it with a really, really brittle intermetallic material, then that's the actual problem that we have here. Yeah. So maybe, that helps a little bit to understand why is this heat exchanger structure so important to get the machine to work and also to have a high effect and a high cooling power.
Yeah. So you said that this was made with laser additive manufacturing.
Yeah.
Is that the way to manufacture it when going industrial?
Probably not. Or, yes and no. So usually laser melting is not really the method you choose when you go industrial, right? That's why you're asking probably.
Yeah.
In this case, as you will not, or at a moment or during the next years, you will probably not use tons and tons and tons of magnetocaloric material. This could be a good technology for the next years and to get the technology started, because actually the laser melting is working really well, and we are very, as it's additive manufacturing, we have the option to make many different shapes. And so you have the option to also to try many different shapes. Maybe Christina can also show, we have some pictures of structures we made, and you can make round structures, you can make different channel sizes. You could also have like an internal design of the channels to have a better heat exchange. Yeah, let me just wait till she gets the pictures. Yeah, exactly. So here you see some of the structures that we did by laser melting. Of course, this is not really fancy additive manufacturing, a lot of different fancy designs, but we have different channel sizes, we have different outer structures to use it in different magnet arrays. And so we can try a lot of things and see what is the most efficient. And I think as long as the technology doesn't really isn't really used in high tons of material, this could be a really good way to get these structures. But actually, of course, if you really want to industrialize it and want to build fridges or coolers that should be in every home, then you should use other technologies. And actually at IFAM, we are looking at metal powder extrusion for these kind of applications. And this is a real technology for industrialization. So
basically,
I agree on that.
What a surprise, Peter. No, but so I think we do not toss additive manufacturing as an idea, because it has so much potential also for trying a lot of things, for trying a lot of structures. We had a PhD who worked on a certain kind of structure, internal structure, and this was only be realized via additive manufacturing, right? So it always has its own benefits. And I think it's not at the end of development, of course. So who knows what will be in 5 years. But for now, as we are having companies that try to sell this kind of structures on a larger scale, on an industrial scale, of course, we have to, as an applied researcher, we have to find ways to produce fast and reproducible just in a faster way, in a very reliable way. And of course, then you always end up at the end of the day at when you look at powder metallurgy, is it like press and sinter, is it MIM, or is it powder extrusion? And for us, for this kind of parts, because they can be quite long, depends on the application you have. You end up at the extrusion process, and that is something that we have done in the last 7 years, basically 7-8 years. I think even longer. Before I came, it was a thing already. So, and what we do is we prepare the feedstock. Again, the powder is bought. So we order the powder, and it will be produced to our wishes, basically. So depending on the client who comes to us, says, okay, I want a refrigerator for room temperature application, then we will buy the powder accordingly. And we take this powder and we make it into a feedstock. We put it through the extrusion process, and we extrude the part itself, the green part, right? And then afterwards, of course, you have the sintering and the heat treatment. Again, sintering and heat treatment, very important. I mean, sintering, of course, because you want parts that last, and the heat treatment because you want to have the effect. Again, remember that it doesn't have the effect when it comes out of the extruder. So you will need to have to do the heat treatment. And this is just some examples of parts that we have done in the last years. You can see some structures that have been done together in a collaboration for the Schunk company. I think you know them as well. So they approached us for this kind of technology, and we wanted to make heat exchangers on a large scale. So please have in mind when you look at those pictures, especially on the left side in the down part of the slide, these are cut by hand. Okay, it's not a machine cutting process. So it was basically me cutting this, and you can see basically every millimeter which I was left or right. So if it doesn't look perfect, it's because I'm not a perfect machine. So on the left side you can see the green parts after extrusion, and in the middle you can see the parts after sintering. And what is the nice thing here is that we extrude one of those slides, basically one of those strings. How do you call it? Like a long, string. Strand. Thank you. Close enough. And then you just stack them on top of each other. And when you put them in a sintering furnace, they sinter together because they are the same kind of material. And at the end of the day, you are like this, you are building your heat exchanger. Okay. Because it's very hard to do tooling for this kind of small microchannels. We tried a lot. It gives you a big headache because it never really works. So we were like, okay, we have to go back to the drawing board, and I think this is a good way to go. Okay. On the right side, you can see those little channels that we have realized by stacking the different parts that we have extruded, and they look very nicely. I mean, it's I'm just like a proud mother. And basically, that's how you do your heat exchanger.
The sintering and the heat treatment, is that done in one run, or is it two different?
Yeah, it's this is basically done in one run, and it's also like the I mentioned it. That was my PhD topic, to find the temperatures and sintering times that match both the needs of the sintering, so the densification, and also on the other hand the phase formation, because the temperatures are actually close where the densification and phase formation happen, but they are not the same.
Okay.
So usually the phase formation would need a little bit lower temperature range than the sintering needs. And that was part of my PhD to see how you can combine both to have it in one process.
And again, when you that's why you need to put in some research into it, because I mean, you want to be as close as possible to each other, because you don't want to spend too much time in a sintering furnace doing the sintering and the heat treatment, and you don't want to have a contradiction in results. You don't want to have like a very stable part but a low magnetocaloric effect. And usually it's always some kind of trade-off you have to do. You either have like a very strong part that has a very much part of a magnetocaloric active phase, but then usually at the moment where the research stands today, you will have a brittle part. So you have to always make some kind of compromises for stability and effect. And this is still an ongoing development. And especially when you look at the industrial application, you always need to have the same kind of source material to have the same kind of result at the end of the sintering and the heat treatment, in order to be able to put it in the fridge and say, so this always has the same effect. And this is really, that's the challenge.
I have several questions on my tongue now. The first, I learned about this cascading, Sandra, you said. Can you build in the cascading effect in the extrusion process or in the laser additive manufacturing process?
Theoretically, you could, but it's not, you shouldn't, as if you have the heat would flow through the whole magnetocaloric material. If you have it a strand in extrusion, if it was just a long strand with different Curie temperatures, but the temperature of the material wouldn't stay at the part where you have the Curie temperature of 5 degrees and 7, but the temperature would even out through the whole strand.
It will be homogenized.
Okay.
So what you need to do is during this cascading, you need one small part which has a Curie temperature of 3 degrees. Then you need some space in between, and then you take the next Curie temperature, because afterwards, otherwise the temperature will just even out, and then it will not be working. So it would be possible from the methods that we use, but it's not useful for the magnetocaloric device.
Okay. So you are using you're guiding the water into different systems when the temperature changes instead of so that's the cascading method.
So you will have one part of magnetocaloric material which has a Curie temperature of, let's say, 5 degrees. At 5 degrees, and then the water will flow through it and will heat up from 5 to 7 degrees. And then it goes into the next magnetocaloric material and will be heated up from 7 to 9 degrees, and so on. But if you have these two magnetocaloric materials, if they are put together, it would even out, and all of the magnetocaloric material would be at 6 degrees and not at their working temperature.
And also when you think about, again, industrial application, I think you would introduce a lot of possible points where you could have some issues with the material if you say, okay, I will just do the extrusion process and I will add, I don't know, more manganese with time, so that the Curie temperature in the strand itself, when it comes out, will have different values. So when you go look at the industry, you will have the process like this, that they will, I don't know, they will produce a feedstock of 500 kilogram per batch. And then they would just put it in, extrude the whole thing, and then they have 5,000 parts. And then they will measure those parts for the effect and the Curie temperature itself, and they will put it into a shelf, basically. And if you would start now, because I feel the way of thinking what you say, because it feels like the elegant way to do it, right? But I think it's not very applicable for a large scale production process.
I fully understand. Then this is lanthanum material. As I understand it, it's very sensitive to oxygen, to corrosion. So the sintering process, is that important to be as clean as possible? Is the effect strongly affected by oxides, or is it, can you do whatever you want and have a lot of inclusion and it still works?
No, because it's very important to be clean. One point is oxygen, as you mentioned. If you get a lot of oxygen into the material, you will form lanthanum oxide and will not have enough lanthanum to form the phase that you want to achieve. So then you will not be able to really form the phase that you want to achieve, because all of the lanthanum is going into the oxides. So you need to make sure that you don't get too much oxygen into the powder. But we have to say that with the particle sizes that we use for extrusion, for example, and also for laser melting, the powder is not so sensitive. When we take atomized powder, you don't have to handle it in argon atmosphere or something like this. So of course you have to sinter in argon atmosphere. But you don't have to handle the powder, for example, in protective atmosphere. It's fine to just handle it in air. So this is okay, but this is the oxygen side. But when we talk about these kind of processes, the extrusion process, we also need to talk about carbon and impurities, and it's also important to don't get a lot of carbon into the material, for example, because this will change the Curie temperature actually. Then you will get different Curie temperatures than expected if you have too much carbon.
Unexpected cascading.
Yeah. So it's a way you could use this to cascade, but maybe not the way you want to.
Yeah. And then if we look at the application where you have water running in it, you said that you had some inhibitor in the water, but is it very sensitive towards corrosion? Do you need some surface protection or how is it?
So usually, so everyone does this in a little bit different way. So if you have perfectly all over the whole material, you would have the magnetocaloric phase for lanthanum iron silicon. It wouldn't be such a big problem with corrosion. But what you usually have is you have some iron leftovers. There's some residual iron, and this is of course very sensitive for corrosion. So and so you could have different ways you could coat the material. There's actually one of the companies who produces magnetocaloric coolers. They have a patent way to coat these structures so that you make sure that it's not corroding. But others coated with some very thin layer of polymers. But as I mentioned before, if you have some inhibitors in the water, and if you manage to really have a low amount of iron inclusions, maybe you can even be fine without anything else. But I think most would coat it for just to make sure that your machine is really working over the years.
Yeah. So if we look into potential applications, it looked very fancy. So is it something you can have in your home, in your fridge at home, or where are the applications?
So first of all, you can buy this kind of cooling machines, cooling devices. There is at least one company in Germany who sells this kind of fridges. And they are usually at the moment, and I don't know all their customers, but I've seen, them on LinkedIn and everything. And they usually sell them at some kind of display fridges for supermarkets. So when you're standing in front of the cashier, you can grab like a Red Bull or something, and they always have some kind of special fridges. This is the kind of fridge they sell at the moment. But they, as far as we know, we don't want to, we don't know everything. As far as we know, they do not sell like at-home fridges. And that's something also that we do not see in the near future. Because we have it's just not the stage for the state of technology yet. And also when you look at the home freezer device market, it is very price sensitive. And at the moment, this kind of magnetocaloric cooling systems, a major drawback is that it's quite expensive, not only because it's always like a prototyping system, but also when you look at the magnets that you need, and Sandra told us already that it has to be like about a Tesla of a magnetic field. If the magnet costs 500 euro for your fridge, what does the fridge cost at the end of the day? So, and I'm sure a lot of people can't afford that for a good reason. So they wouldn't buy it. So for us at the moment, we think there are a lot of applications for this kind of cooling. It can be used in heat pumps or as a thermogenetic generator. So there are a lot of applications for the material itself, but we do not see it as a home refrigerator system. We can see it or if you do your research, like you Google the system, you can see that it is being used as a wine cooler, as example. I think this is the most prominent example, or was in the last 10 years. I'm not even sure if you can still buy it, but I think it was the first system that was available to purchase. And a wine cooler, of course, I mean, I'm sure it was chosen because the temperature range isn't that high. And the price sensitivity, I mean, who has a wine cooler? Is, I mean, I don't have one, but I think it's a kind of a luxury item anyway, so people are not as price sensitive towards it.
And the advantage is that it's no noise. Does it have a high efficiency, or where is the advantage?
So in principle, that's something we maybe should have started with to say, why would you even use it? In principle, it could be like around 30% more efficient than a compressor system. So, and if you look at the world today, where a lot of energy is going into cooling of all different things, and most probably there will be in the future even more energy going into cooling houses, into cooling everything you need, then this is really important that if you really achieve to have this 30% less energy consumption than the systems have now, this would be a whole lot of saved energy. So this is the biggest pro for magnetocalorics. And the company that Christina mentioned that is also producing such kind of systems and selling them, they say that they measured 15% less energy consumption than the devices the supermarkets had before. So they can already show that they can save energy with this technology. It's not as much as you can theoretically save, but it's already, 15% is something. And it's showing that there are options. In a real life setting, exactly.
It's not a lab data.
And then you have some other good points. For example, for magnetocalorics, one thing that's always mentioned is that in compressors you have the coolants. They are they have a high global warming potential. So if they get out of the fridge into the nature, then you will have a very high global warming potential for these kind of gases. And some of them will also be forbidden in the near future, and there need to be other ways to probably most of them which will be forbidden can be other gases will be used as coolants in compressors, but there's always the problem that you have a high global warming potential, and for magnetocalorics you just need water as a cooling fluid. So this is another pro point. And what you mentioned, that these systems can be less noisy and less vibrating. This is also something that is often mentioned. It could be important for some medical applications, for example, or for some electronic applications,
laser cooling.
Laser cooling. But there we have to be honest, the prototypes that we saw so far, they were not really that quite. They were but prototypes.
Fair.
So there are a lot of things that could be really, really good when you use magnetocalorics. But as Christina already said, I think the biggest point at the moment to really use it in broad applications is that you use this kind of really big magnet, which makes it quite expensive and also heavy, to be honest. And so this is limiting the applications for private customers. But I think for supermarkets or for electronic cooling and this could be really applications that are really interesting.
And that's also why we, Sandra and I, we are trying to make this topic known and to push it also a bit. Is that we as researchers, we do not just do research for the sake of research, right? Because we want to see this this technology in action. I mean, it's not that we're sitting at our desk the whole day and, wait for a miracle to happen. So we really need the industry come to us with applications, because we are sure that there are applications. I mean, there's a huge potential when it comes to energy saving. And there are a lot of applications that we just don't know because we are just two people. And in the later times, it was always like, a company came to us, or it's still like this. They come to us and say, we have this kind of application. It needs to be called. What can you offer? And that's where we come in. And then we do some kind of, consulting and everything. So we do see applications. It's not the household application, but there will be, like supermarkets. I think it's the best example, because there you have a small temperature span outside of the system, because supermarkets usually they have, I don't know, it's like 22 degrees, something like this. So it's not that you have like a 40 degree in the summertime in a supermarket and 10 degree in the winter, but you always have like some kind of stable outdoor, let's say, out of fridge temperature. And for this kind of cooling devices are perfect.
Perfect.
Just to have a little love letter from Magnetocaloric.
We have come to an end, but before we end, I would like to ask, where could people learn more? Are there conferences? Are there papers? Where should they could call you, of course, but where could they find information about magnetocaloric materials?
So, of course, we will provide you with some links, and you can put them in the show notes. So if people are interested, they can, of course, contact us. We are always happy to nerd with somebody else about the topic. So just, contact us. But if you want to have some conferences, it would be actually very soon. I don't know how fast you will upload the video, but in November, there will be the Delft Days of Magnetocaloric. It's November 20th and 21st, so it will be, I think, next week. I will be there as well and present something scientific. And it's really nice to meet the community. It's not a large community, so it's really like it's very intimate setting. It's really nice. And also, of course, you have the Thermac in Ljubljana, I think it's on English, in June 2026. So this gives you some time to, plan your travels. And this is really like the world's largest conference on magnetocaloric materials. And it's always very well organized. It's a really nice conference, really. I can just recommend it. And of course, we have...
Let me step in just for a sec. Actually, it's a conference in all kinds of caloric effects, because maybe this is something we can also mention. It's not just magnetocalorics. There are also some other caloric effects who work similar. So, for example, there's an electrocaloric effect with electric fields. There's an elastocaloric effect. They all will be discussed at this Thermac conference. So I think this is also, all the other effects are also interesting, just to have them also mentioned in this, because they are all interesting for applications, actually.
And of course, if you want to have a book and read something about it, so it's not from us, so we don't get any royalty. But that's basically, the Bible. Everything stands in there. It's from Andrzej Kitanowski, who I think will also be the conference.
This is a really great book. So there you learn a lot.
Thank you very much. I really enjoyed it, and I learned a lot of new things today. Some of it I cannot pronounce, but hopefully my guest will, or the police will take it in their next task. Thank you for joining in.
You're welcome.
Yeah, thanks a lot for giving us this option. It was really fun.
Yeah, we hope we didn't confuse you too much. But if yes, and you can't sleep, just call us.
Perfect. Thank you.